Welcome everyone. This is the inaugural Room 211 talk by Abu Baida Shabat. This is a tutorial session, so it's going to be a two-period session, so get settled in. And we're going to be talking about image classification. I assume that this is in Python, or it wouldn't really make much sense. So we'll have questions at the end, and just make sure that you wait for the mic to ask the questions. That just makes it easier for the video later, so people can understand what's going on. So let's get started.
Okay. Good morning, everyone. My name is Abu Baida Shabat. I did my bachelor degree in computer engineering in Yemen, and also, okay. Okay, hello? Perfect. Also, I did my master degree at UKZN in image processing, computer engineering, and also I'm doing right now my PhD. I'm almost done in April. So today we will start image classification. By the way, excuse my language, so if there is something not clear or anything, just please stop me and we will go through it again, okay? Okay, for the image classification, it is two-step. First, we have to have the data before any classification for sure in machine learning. So today we will take the textural images as a data set, and then the next step is the feature extraction. What is the feature extraction? We use the feature extraction to reduce the dimension of any image. For example, if we have one image, for example, if the size is 500 by 500, which means we have 2,500 pixels. So it is very big to deal with it, especially when we have a big data set. And for the classifications, we will have a training data set, and we want to know what unknown test. Okay, as you see here in the figure, as I said, the steps is you have the textual image data set. We extract the features. The features will give me, we will come to it later, and then it will give me features factor, and after that we classify, and then we get the final result. Image classification can be used in medical, it can be used in security, in remote sensing, in different type. And since it's a practical one, let's go for the dataset. What is our dataset for this tutorial? Okay, as I said, we will use the textural image, and we have 3,200 images from Kilberg textural dataset, and it is divided into 20 categories, and each category have 160 images. And sure, all the images is 576 times 576. And if you see, this figure is just a sample of each category that we are going to use. And before we go to the features factor, just to make sure that everyone knows the basic of OpenCV, I'm using OpenCV Python. So the first thing that we have to use, if we want to use OpenCV, we have to import CV2, and also for sure, since we are dealing with pixels and matrix, we have to call NumPy. For example, if I want to read any image from any file, I hope none of you is hungry today, or this is Arab food, by the way. Okay, so to read an image, very simple. You just call the cv2.mread and then the image. This could be URL, file, whatever. And we call it image color, which means we save this image with the 3 channels. Remember, in any image, we have 3 channels, RGB, red, green, blue. Now, if I want to get the gray, and usually when we deal with feature extraction, we don't need the colors. Usually we deal only with the gray level. So, if I want the gray level, very simple, I will just say cv2.mread and then the image, but this time we put 0, which means only channel 1, which is the RGB, the gray level. Now to show this image, let me just first run it, sorry. Oh, okay. Because we didn't play the import. So first we import the CV2, and then we use it. We use the mread function. So now we have two images. The first one with the 3-color RGB color, and the second one, it's only the gray level image. Now, if I want to show this image, in OpenCV we have a function called mshow, and then the window name, and then the variables that save my image. So the first one I said cv2.mshow, and then the window name called it colored image, and then the variable which is image color, which is our image, which is the RGB image, and also cv2.mshow, the gray image, and then we put the weight k to destroy the windows. Let's just run it. Now if you look here, we have two images. The first one is the RGB one, which has all the colors RGB, and the other one is the gray level one. Also, if you want to check the image size, how many pixels we have in this image, the first one, if you want to know the size or the shape of the image, we have a function called .shape. And also, if we want to know the numbers of pixels, we have image.size. So let's first see the image.shape. Now when I run it, it gives me first the dimension of the image, and the 3, it means the 3 colors, RGB. And the image.shape, the other one, it's a gray one, so it's only bring me the dimension of the image without the colors. Also, if I want to know the size of the image, very simple, I'll just say image.size, which will show me how many pixels I have in each image. So if I run it, so in this image, we have, what is the number? It's 240,000, right? Yeah. And that's, as I said, it's difficult for us to deal with the image, with the whole image, because it has a lot of a large number of pixels. So that's why we use the features factor. We will come to it. Also, if you want to save the image into a file, .png, for example, here. So we just say cv2.mwrite, and then what you want to name it, whatever is the name, and then the variable that you want to save. And now you will save it. Okay, since any image is a matrix of pixels, we can access all these pixels if we give him just the index. So for example, if I want to print the whole image, I will just say print the image. Remember, this is the gray image. It's already run, but I should reset it, but anyway. Okay, so now we have the image. If I want to access to the index 200 and 200, very simple, I will just say print image, and then this is the x-axis, and then the y-axis. So we have 200 and 200, and it gives me the value 156. Also, if you want to change the value of the pixels, very simple. Let's go down. If I want to change the pixel value, I have the image, and then I go to the index x and y, and then I give him the new value. For example, here, I go to the index 200, the x-axis, and the y-axis is 200, and I make the value. I replace it. Instead of 156, now become 30. Now, if I want to check if it changed or not, I'll just, very simple, I'll just print it. And now it print 30. Okay, also you can crop a piece of the image. Maybe you just want the above part, or the down part, or the half, or the middle part. It depends. If you know the index, you can get it. So for example, here I crop the image from the 200 pixel to 390 for the x-axis, and for the y-axis, I take it from the 200 and until the 390. And now I can show it. Let me just see it. Yeah, and it takes just a small piece from the original image. Also, if you want to split the colors from the image, for example, you remember that image, we have the RGB colors. Now we can split it. We can take the blue by itself, the green by itself, the red by itself. We use a function called split. So here we have the B, which is blue, G, green, and red. The red is equal to CV2.split, and then the image with the colors. So for now, for example, if you want to print the blue one, very simple, just the B. And also we have this, the G, and we have the R. And also if we want to return it back, if you want to merge the colors again to the original image, very simple, we have a function called merge. Anyone has a question for this basic OpenCV? Yeah?
Is the y-axis from the top to the bottom or bottom up?
The x-axis is that vertical.
Yeah, but does the y-axis go from top to bottom or from bottom to top?
Sorry?
Where is 0 on the y-axis, at the top or at the bottom?
Okay. Let me draw it. Okay, so for any image, can I draw here? Oh, okay. Sorry. Okay, so here we have 0, 0, 0, 1 until, for example, if it is 400, and then we have the 0 to 400. This is answer your question. Okay. Okay, now we just know the basic of OpenCV. Now let's see the features factor. The extracting feature. Sorry. So the features factor, feature extraction, sorry, we start with the GLSM. Okay. Now for the GLSM, it was proposed by Haralick in 1970, and it is a statistical way, which, let me just even draw it. Sorry. Okay. I think it will be easier when explain it here. Oh, I have to. Okay, let's assume that we have this image. As I said before, the purpose of the extracting features is to reduce the dimension of the image, right? Because, as I said, if we take the whole image, which, for example, is if it is 500 by 500, it means I have like 250,000 pixels. So, to solve that, we have the feature extraction. The first one was proposed by Haralick in 1970 to reduce the dimension of this image. Let's assume this is the image that we have. Now, if I want to extract the GLSM, very simple, I will look for the pair pixel, the frequent of the pair pixel. So, for example, by the way, the gray level here, the maximum gray level here, we have what? 8. 8. So that's why we build our matrix here. 7, 8 until 8. So as I said, we look for the pair of pixels, the frequent of the pair of pixels. So let's start with 1, 1. If you look here, how many 1, 1 we have? By the way, this is 0 direction, because we're going 0 direction, right? So 1 by 1, how many pair of pixels we have here? Is it 1? 1. Sorry?
There's a couple diagonal ones. The bottom right.
Right.
A couple of diagonal ones.
Yeah, but we take first the direction 0. Okay, so for the first direction 0, we have only 1. Now for 1, 2, 1, 2, yeah, we have this one, and we have this one, right? So we have 2, the frequent. And from 1 to 3, we don't have, so I think it should be 0. 1 to 4, and we keep going. So we know what exactly the frequent of each pair of pixels, the neighbors pixels. This is for only direction 0. For example, if we take the 45s, the 45, what it means, it means you take 2 to 1, 3 to 5, 5 to 6, 7 to 8, 4 to 3, 5 to 5, 7 to 7, 1 to 1. Also, we can take the direction 90, which will be, yeah. Or we also can take the direction 135, which will be the other side. So the GLSM, it has 2 important parameters. The first one is the direction. And we have 4 directions, the 0, 45, 90, and we have 135, right? Also, there is another parameter. If you look at this one, we only take the distance 1. So we go from 1 to 1. So we have another parameter, which is the distance. And it could be 1, 2, or 3. So if it is 2, then we compare 1 to 5. Okay. Anyone has a question with this part?
What direction in the next row? How does it work when you go 2 to 1?
2.
Right now you're dealing with the first row. In the second row, how are you going to resolve, let's say, the 2 to 1 or 2 to 3? How would that work? 2 to 1?
2 to 1.
Yeah, how do you draw that?
In which direction?
The 0 direction.
0 direction. 2 to 1. To be 0.
So, okay.
Since we don't have any frequent of 2 to 1, it will be 0. Okay, so we have now 2 parameters. The first one is the direction, and the other one we have the distance. So when we said, for example, direction 0, but the distance is 2 this time, it means you compare 1 to 5, not 1 to 1. Okay, because this one is distance 1, and the other one is distance 2. So we have 2 directions. So after we compute the GLSM, it generates this function, right? Which will be 8 by 8. But if you look at the original one, what is the dimension of this one? 0, 1, 2, 3, 4. So how we reduce the dimension from the original one? Now we make it more even higher dimensional, right? Now become 8 by 8. So in this case, after we compute the GLSM, we have 14 features, which is the hierarchic features. You compute it from this matrix. Let me just show it to you. Okay, so after we generate this image, the transformed image, now we can compute 14 features. So after we compute these 14 features, what will be the result? It will be a factor f0 to f13. This will represent my image. Only one factor with 14 items. Anyone has a question? If it's not clear, please. Yeah.
Do you generate then the bottom matrix? Is it the direction multiplied by the distance? Is that how many of them that you get?
Yes.
Is that right?
Yes.
Okay.
You see, no, because you see, even for the 14 features that we generate here, we could generate it for 0 direction only, or we could generate it for 45, or 135, or 90. And even you can get the average of all directions, even the distance. You can get for this image, let's say, four factors. For each one of them has a distance 1, distance 2, distance 3, and distance 4.
Okay.
So these parameters, you have to play with it until you get the performance that you want. It depends on the application that you want to use.
Okay, thanks.
Okay. Okay, so let's implement it. Let's see how we do it. By the way, I didn't implement this. It's from Sky Image library. So first I call the CV2, OpenCV, and then I call the NumPy, and then the Sky Image.feature, and I call it as SK. So the first thing, I read the image. Let me just run it first. And then, sorry, I read the image as a gray image, and remember the example. And then here I do the gray comatrix. So the first parameter was my original image, right? The second parameter is the distance. And here I choose the distance as 1. And then the direction. I use the 4 direction. This is the direction 0. This is nb.pi multiplied by 4, divided by 4, it will be 45. Then we have 90, and then we have 135. So I generate for 4 directions, yes, but in distance 1. And if you look at the image, here's our image, the original one. I didn't run it there. Okay, just run it. So this is the original image. And this is for the 0 direction. This is the GLSM matrix, which we see in the second step. Then all what you have to do, then you compute the 14 Haralick features. Anyone has a question with the implementation? Yeah?
How do you compute these 14 features?
Yes, okay. I didn't write it down, but let me just bring it. Document. GLSM, yeah, okay. The main one. Okay, this is my code, so let me just bring the features. Because I was going to show a practical example, but okay. Yeah, here's it. We use here Mahotes. Mahotes, I don't know if the spelling right. Let me just call it. Yeah. And then let me just bring the Haralick features. And this will get the average of the 4 directions. Yeah, it is not image, it's AMG. Okay, so now if I want to check the F14, no, it doesn't write down. Now we have the 14 features of my image. We will come back to it. But anyway, so we use here, I use Mahartos library, and it has the features .haralick, and then this is the original image, and then it will give you the average of the 4 directions. Okay, anyone has a question? Okay, we go to local binary pattern, and I think most of you is maybe familiar with it. I think my voice is strong. Can you hear my voice?
It's mainly for the video.
Oh, okay. Okay, so for the local binary pattern, it's another features extraction, features method, and it was introduced by Ojala, and it is a 3 by 3 pixels window. Okay, so let me just go to the example. Yeah, I think it's clear even. Okay, so we have this image, which is, I think, rice image. And we take this window. It's a 3 by 3 window. And it has this pixels value. So the local binary pattern, how it works, he take the center as a threshold, which means any value for the local neighbors greater than the center value, it should be 1, otherwise it should be 0. So if you look at this example, the center value for the 3 by 3 window is 41, which is the threshold. Now we compare it with the first one. 25 is less, so it should be 0. 30 is less, so it should be 0. 15 is less, it should be 0. 55 is greater, now it should be 1. 45 is 1. And now we have what? Now we have a binary code. Now when we change, what we will do, we change the binary code to be a decimal code. If you look here, we multiply it with this matrix, which present 2 power 0, 2 power 1, 2 power 2, 2 power 3, just to get the decimal. So you multiply this binary code with this matrix and will give you the 88. Now what we will do with the 88, we replace it with the center value. So now what we have 55, 15, 30, 25, and now it's 88 instead of 41. And we keep going inside our image. This is just a window from the image. The next image, it should be, now if, for example, it was 41, 50, and now we have 40, and now let's assume that we have 10 here and 20. So we take this window first, and we apply local binary pattern, and we convert it to be 88. Now the next step is to go to the next window. And now this one will be the threshold for this window, the next one. And we have also to convert it. So now after that, we have a transformed image. Not like the original image, it will be transformed image. And in the transformed image, what we will do, we extract the histogram. And since in any image, the maximum gray level is 255, so the histogram should be from 0 to 255. So it will generate a factor for this image, just one factor, starting from 0 to 255, which will represent our image. Any other question? Yeah.
That's for the whole image. There's one number that represents the entire image. Okay, so after you've done all your scan, then it's the middle one of the last square.
After I do the all scan, I will have now a transformed image. Because we change, remember, always the center we change it. Then after I have the transformed image, I multiply the, I extract. After I have the transformed image, I extract the histogram. The histogram, it should be, since our image, it's range from 0 to 255. So if we extract the histogram, it should give me just one factor, which is started from 0 to 255. Anyone has a question? Okay, we go next. Yeah.
What would be the maximum number if you had ones all over that matrix?
Sorry?
If you had ones all over that matrix, or you get 255 maximum.
Okay.
If you had all ones in
Yes.
the matrix and you transformed it with that binary conversion to a number,
Mm-hmm.
the maximum number would be.
But remember, this is a histogram. The histogram, it means how many times the pixels will represent. So, for example, the pixel is 255. How many times will be repeated?
My question is,
Yeah.
what if you get a threshold where you get all ones? How many of those? 11 ones.
Okay, the right question for what you're asking now, what if I have it, which means the threshold is the minimum value, right? And everything is the maximum value, which means we have 1, 1, 1, 1, 1, 1, 1. This is why local binary patterns is not reliable when we have an image with noise, or if we have, for example, the facial expression. Any change in the image, it could affect the result, right? So that's why one of the disadvantage of local binary pattern, it used the uniform code, which means, what if the center value is less than all the neighbors, which means we have 1, 1, 1, 1, which means there is no transaction. For example, for that one, we have 0, 0, 0, 1, 1, 0, 1, 0, which means we have how many transactions? We have 1, 2, 3, 4. So that's why we are going to present the next one, which is local directional pattern, to fix the problem with local binary pattern.
Microphone for you.
Oh, okay, that's good.
Back on that, yeah.
And the other question,
Yeah, ask. Keep it with him.
Okay, how do these guys come up with these algorithms? You just play around with pictures and like guess?
No,
This
no.
this doesn't this doesn't look like there was any science applied to how these algorithms are made. It's like we're just counting numbers and guessing. Is
Okay.
that how it works?
The next, no, the second name of the feature extraction is called hand design method, because you have to design it by your hand. And one of the disadvantages of this method, by the way, it's a mathematical because I think, I don't know, that's why I go just for the point. But this is a feature called hand design method, which means you created, let me just show it to you. You see, there is a method and there is what you called it, a concept behind the local binary pattern. But since this is tutorial, I just go through the method itself. But anyway, everyone has a background, math background. Yeah? Okay. So what we will do here, we have a 3 by 3 matrix, right? So what we have to do, as I said, we take the threshold. So how we will do it, we assume that the center is FC and any neighbor's value is Fi. And we use the function called S, Fi minus Fc is equal to 1 if Fi is greater or less than Fc, which makes sense. For example, the 41 will be Fc and any neighbors will be Fi. It could be, for example, this one F0, F1, F2, F3, F4, F5. So what we will do, we subtract the Fi, which is, for example, 25, from the Fc, and if the value is greater than, the Fi is greater than Fc, we put it as 1, otherwise we put it as 0. If you look at the function Sx, it is 1 if the S is greater than 0, sorry, and otherwise will be 0. So the LDB code, how we generate it, it will be what we use here, 0 or 1, and then we multiply it by 2 power I, which is to convert it from binary to decimal. Then we have the LDB code. Okay. Anyone has a question? Okay, we'll go next. Or yeah, the implementation. Okay, so for the implementation, we always call OpenCV just to read the image. And then we import the NumPy for the matrix. And then I create that, the import LPP. Let me just show it to you, the code. LPP. Yeah, no. Yeah, this is the one. Okay, so in this code, we create 3 functions. The main one that I'm going to use for the LPP is called LDB matrix, which take the image and the transform image. And then I go from the x-axis and the y-axis. It will start from 0, since the matrix will start from 0, and the length of the image, which is the x-axis. And then from for y, the y-axis in range from 0 to the length of the image for the 0. Then I take the center value, which will be equal to what? Image x, y, which is the first value. Then we take the top left, because, okay, let me just show it to you. So this one, it's xy, right? So now if I want to go to the top left, which will be this one, what the value will be? If this one is xy. So the x will be -1 if you go that direction, right? And the y, right? And so on. So you can go all the neighbors, the 3 neighbors, the same thing. So for example, x -1. No, to be x, no, to be x, still x, right? But y -1. Also we have x, but this time, I'm confused now. Oh, okay. So we have x and y. So x, y. If I go up, down, so it'll be x -1, y, yeah. Please correct me if I'm doing something not right. So x -1, y +1. So this one will be x and y minus 1, true. Then we have x plus 1, y minus 1. And this one will be x plus 1, but still y. I'm right. And you can continue with. Anyway, so at the first we take the center as the image of x, y, and then we take the top left, the top up, and then we start comparing with, we make the center as a threshold, and we compare it with the neighbor's pixel. So after that, I call the method called the threshold, which take two parameters. The first one is the center and the pixel, the neighbor pixels. Let's go to that functions up. This is the threshold. It has the center value and the pixels. And we declare here the list out. Then I couldn't see. Yeah, for A in the pixels, if A is greater or equal to the center, we make out.append equal to 1. Otherwise, it will be equal to 0. I think it's the concept of LBP. And then after you get the threshold, the out, then you get the weight. You multiply it with the weight just to convert it to the decimal point. And then after you multiply, you go convert the value of xy to the new value that we get, which we call the result, RES. And then after that, we get the histogram. And remember, the histogram is from 0 to 200. And no, it should be 55. Okay. Anyone has a question for the implementation? Okay. Now we go to the local directional binary button. Directional button. Okay, when they propose local directional button, they propose it because the local binary button was affected with the noise and is not reliable when it comes to the facial expression. So now we come with a new method called local directional button. And first, let me even draw it. Go to the example directly. Okay, so the local directional button, how it works. He take the window 3 by 3, and this is the pixel, the original pixels, 3 by 3. But then what he will do, he will multiply it with the Krish mask. In the Krish mask, we have 8 masks. Usually we use it for filtering the image. Let me just show it to you, the Krish mask. Okay, this is the Krish mask. We have 8 Krish mask, and the difference just the direction, the rotation. If you look at the M0 and M1, it's the same thing, but it rotates by 1 step. So we have 8 masks. We multiply it with this window, 3 by 3. And then for each mask, we get a new value. For example, we get M0, M1, M2, M3, M4, M5, M6, and then M7. Let me just show it you up. Okay, you see what we do? We multiply the 3 by 3 with M0 first. After we multiply it, we get one value. Let me even do it. Let me just show it to you. So now we have this matrix, the original one. Okay, so the first thing, how we get, for example, the 290. We multiply this one with the first mask. I think it's minus 3, minus 3, minus 3. 5, this one is 0 for sure. 5, 5, 5, minus 3, minus 3. So this is the first mask, M0. So how we get the first value? Very simple. We go, M0 will be equal to what? Minus 3 multiplied by 55 plus minus 3 multiplied by 15 plus minus 3 multiplied by 30 plus 45 multiplied by minus 3 plus 60 multiplied by 0 plus 25 multiplied by minus 3 and goes on. And the result, it should be minus 290. This is just for the first mask. And remember, we have 8 masks. So we have M1 until M7, right? So, so now if you look here, this is M0, which multiply the original one with the first mask, it would give me 290. And if I multiply it with the second mask, it will give me minus 250. And so on. Then after that, LDB, how it works, you choose the K as equal to 3, which means he choose the 3 maximum value from these values and convert it to 1, and anything else will be 0. So if you look here, minus 290, and by the way, we take the absolute value. We don't care about the sign, is it positive or negative. So the 3 maximum value here is 290, 310, and 270. So we convert it to 1, and anything else will be 0. If you look here. And then, of course, we have a binary code. Now we multiply it with the weight to get the decimal value, and we replace it with the center value. And then after that, exactly as we do in the LBP, we get the histogram for the transformed image. Anyone has a question?
Can you show us a picture of what that transformed image looks like, or is it just looks like noise?
No. I will show it to you. Even the LBP, we should show it to you. Okay, let's do the LDB now, and then we go back to... Okay, so let's see an example, how it looks like after we apply the LDB to it. So let's just run it, and... Okay. Now, if you look at the original image, and for the transformed image, what do you notice? It shows us the edges. Any edge in the image, it shows us. Look here. Look at the edges here. Even I'm going to show you an example. As I said, we tried 3,200 image, and we make the training value as 80% and the test as 20%, and the result was 90-something. The performance, I mean, the accuracy. Okay, this is for the LDB. Also, we didn't see it for LPP. Let's even see it for LPP. I don't know why I stopped there. Okay. If you look here at the LPP, you see the difference between LDB and LPP. This is the original image, and this is when we applied the LPP, the local binary pattern.
Also edges.
Also edges, yeah. Oh, anyone has a question? We could continue. Okay. Yeah.
Sorry. If you ignore the sign of in the matrix, why is it there? In the transformation matrix that you used in LDP.
Why we
you've
ignore
got
the
negative 3s?
Yes.
Why even have the sign there if you're just going to ignore the sign? Yeah.
Yeah, because you see, he applied the filters, and the filters I don't know if you are familiar with the filters. The filters, if you calculate the value of the filters, it should be 0. Look at the filter. Now we have how many minus 3? We have 5. So 5 multiplied by minus 3, it should be minus 15. And how many 5 we have? So 5 multiplied by 3, it's 15. So the sum, it should be 0. Any filter? Oh, sorry. For the Krishma, oh. I'm not used to it, so yeah. So any filters we use in image processing, it has to be, the sum of it is 0. That's why we have to have the minus value. Okay.
Right? Because it's matrix multiplication. So if you multiply two matrices, it's
By the way, about the sign, we publish a paper now, a new one. In the LDB, he assumed that he take just the absolute value. But what we did, we take the negative, the positive, because you see, the negative and the positive, it means it's different edge. So we applied the SLDB, called it, signed local directional pattern, and it improved the performance by, I think, 13%. When we take the positive directions and the negative directions, we take the average of both. Okay, anyone has a question? Okay, we keep going here. Now let's go to the real example. I think it's my phone, this one. It's in the charger. By the way, if you look here, this is the feature extraction, what I did in my PhD. We create something called CLPP, GLDB, LDBPP, and every one of them improved the performance, and some of them is submitted, but we just wait for the result to be accepted. Anyway, let's go for the classification, and let's see one real example. We still have time, huh? Okay, so let's start with GLSM. Okay. In this one, what I did, I applied the GLSM already for 18 type, 18 category, and we have it saved in the file.pickle. I think most of you are familiar with the pickles. So we save the features factor as a dictionary inside pickle. And then what I have to do here, since I don't have every time to extract the features and again, just save it. So what I have to do here, I just load the file. And here I think I use 8 classifiers. Okay, so I load the first, let me just run it from the beginning. And this is the category I have, the class names. I have blanket, blanket 2, canvas, ceiling, floor, grass. It's textural. But still that one busy with, okay, yeah. And now here. Now remember when you use the classification, you have to have the data and the target. So remember in the GLSM we have 14 features. So for example, if I use the first image, which type floor 1, And it has the 14 features from F0 to F14, right? This is the target, which is the class name, and the features vector, this is, we called it the data. So now, I have the target and the data, and I transform it, so instead it will be a string, it should be now 0, 1, 2. So blanket 1 should be 0, blanket 2 should be 1. I use the transform. Sorry. Now what I did here, remember we have 14 features, but if I take the 14 features and I train my data with the 14 features, some features affect each other. For example, the correlations and the variance, it affects each other, the performance. So what we do, sometimes we take the entropy first, and then we take the contrast, the correlation, variance. So we don't take the 14, because if we take the whole 14, it will make the performance very poor. And then here, the cross-validation, how to split the data. So I have the data, I have the target, remember, it's 0, 1, 2, 3, the data, the class name. And then I make the test size as 20%, and the random is 0. And then here I call the classifiers decision tree classifiers, and I take the parameter as entropy, and the samples will be split by 10. Even I make a for loop, which take all the classifiers. The first one, nearest neighborhood, linear support vector machine, but this time I changed the C value. Also support vector machine support non-linear lineable separable values, like for example, if my data looks like this, this we call it linear separable, because we can create, just draw the linear and we'll split the two classes. This is, we call it linear separable. This is support vector machine, but it has linear. But if my data looks like this, so we cannot now split it using the linear. So what we have to do, we use the kernel to be RPF. Okay, so this is different parameters we use with support vector machine. The kernel first linear, and the C I make it too small, so I don't want it to be overfitting the data. Also the CV here, I use the gamma is 2 and C1. Also, again, the support vector machine, I use it, but this time not linear, I use it as RPF, just to see what performance. And the gamma is 2 and C is equal to 1. For the decision tree, remember, it's like decisions. For example, yes or no. So, yes or no. So when I said the min split is 10, so it means he goes and he starts splitting the tree until 10. You can make it 2. 2, it means he will reach until the 2 children of the tree. But we make it 10 because, as I said, it will make overfitting. By the way, the overfitting looks like this. So the overfitting will be like that. This is, we call it overfitting, which affect the performance. We don't need that. Anyway, so the first one, I take the decision tree and the max depth to split for 5. And the other one, I use the entropy. Also, I use the random forest classifiers, the Adapost, the Gaussian, and perceptron. Let me just run it and show you the performance for GSM. Okay, this is the performance of GSM. And it is very, 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 very weak. If you look here, it is 0.5, this is 72%, this is 5%, this is 34, 34, 38. This one is good. Which one will be? I think it should be the entropy. Also, we have 78, 25, 0.8, and 15%. As you look here, the GLSM do very, very, very badly. But as I said, you can control that by choosing which features from the 14, because it affects, some of them, they affect each other. If you look though, LPP, because I know the time. I did the same thing. I extract the LPP and I save it in a folder called lpp18text.pkl. This is the features factor. And then the class's name. Here I even showed the shape, the data. Let's go down. Then also I split the same thing. I make the test 20%, the random state is 0. And now let's run all the classifier and let's see the performance. But it takes time, I know. And now if you look at this one compared to GLSM, a huge difference. For example, the first one is 97, even 98, and this one is 99. You see, this is also support vector machine, but in different condition. Remember, this is the linear one. This is the RBF. This is when we change the sigma or the C. This is the 0.43, I think it is the NB. But compared to GLSM, it did much, much better than GLSM. Now let's look at the LDB. I display the this is now we split the data. Even I draw the confusion matrix. And now this is without any pre-processing. By the way, we can use pre-processing before we classify. There is one called min-max and the other one called standardization, which means he make each features has the same weight, even if it is different number. And now if you look at the LDB result, for the first one it has 93, the next one it has 99, and as I said, this is support vector machine, but in different conditions, so it doesn't matter. Here is 87, 72, and then we have 19, 86, and 82 for the performance. Let me show you one thing, and we will be done. Where is that thing? LDB. This is we just create, and we're still working on it, but the performance for sure is greater than LDB and LPP. And it's still the same thing. The test is 20, and now look at the result. The first one is 98. The second one is 100. As I said, the support vector machine doesn't matter. The next one is 93. The other one is 77. This is the Adapost. Then we have 90. And then the other one is 86, which is better than both GLSM, LPP, and LDB. Anyone has a question? Yeah.
If you can just clarify what you mean by these success numbers, like did you take
The
a
accuracy.
sample of images and then
The
correctly
accuracy,
predict
okay.
its blanket or what?
So the accuracy is what? Okay, the accuracy is the correct, what do you call it, correct classified class divided by the numbers of the items or the data or the target data. Yeah, data. So you see what is the missed classification and what is the correct classification. Oh, sorry. And then you get the accuracy of this performance. So you see how many missed classification, how many correct, and you divide it by the whole data. Sorry. And then you can get the percentage. Get me? It's not clear.
I think it's clear. Just do you train the system with 20 samples of rice and then you check 100 samples of rice?
Do you know
and-
how we use our data here? Okay, our data here, what I try, I have 3,200 image, which divided to 18 category. So we have blanket, glass one, whatever. So we have 18 type, and and for each category we have 160 image, 160. And for sure, the classification, the more data you have, the more performance you have. Anyone has a question? Okay, so no questions. Okay, that's it. Thank you. Yeah, done. Thanks. Thank you.
Thank you very much. Do we have anything else to close off? Just now that we got to the end, everyone fully in comprehension?
Notebooks be available for us to download and play with?
Well, the question there was, will the notebooks be available? Will you be sharing these so people
Yes,
can go and
yes,
play
no
it themselves and have a look?
Yeah, it will be available. Yeah.
I'm sure.
But
that-
not the last thing. Just the LDB and LDB GLSM.
No, not the ones which you're developing in your new publishable ones. So, yeah, we got another one down here.
Hi. What is new about your PhD work? Because image classification has been there forever.
True, but none get the 100%. None. For example, always we have the missed classification. For the first one, they created GLSM, and when they created it, it was a hot topic because it only gets 70%. But then the local binary pattern came, and now we start reaching the 90 and 80 something. And then the LDB ranges from 90 and even sometimes 80 to 90, maybe 3 or something. My PhD, we reached 98. Yeah.
On
We
existing
improved the performance.
systems that are out there, you are saying the highest that is there is currently 90 to 93.
Yes.
And what you are seeking to do with your work is go
Is to
around and-
improve
yeah,
the
yeah,
performance.
Okay, cool.
And not only that, we are not only seeking the performance, the accuracy, I mean, also the time. Because if you look, GLSM very fast. Local binary pattern in the middle. LDB is very, very, very slow. So even we create something using the GPU, we use CUDA to improve the performance of LDB. And it works for us. Even when I tried, even if you look my LDB code, I didn't show the LDB code, by the way. I implemented Fortran with Python because, you know, Fortran is even faster than Python. So I implement the LDB using Fortran with Python. Believe me, it takes me before with Python, for example, for let's say 400 image, it takes me maybe 20 minutes to compute. But now with Fortran, it takes me maybe, 10 10 seconds. Yeah, it's a huge difference, huge. But this is one of Python disadvantage, which is the slow. Okay.
Yeah, anything else? Yes, back there.
Testing. 1, 2, 3. There we go. Cool. So CPython is very slow by default, and Jython and such are of various hit and miss rates depending on what you're doing. PyPy has naturally seen a hell of a lot of speed integration in the last couple of years, but stuff like BLAS or Fortran integration might not be there yet. Have you played with any of that at all? Does it make a difference for you?
What is it? What language?
Like in PyPy, the alternative Python interpreter?
NumPy, yes. I use NumPy with Python.
No, PyPy.
PyPy, no, I'm not familiar
Okay.
with it, to be honest. No.
So that will give us a just-in-time compiler and things like that to optimize. So it might help you out.
No, I will check.
Cool.
For sure.
Anyone else? Great. I think we're finished then. Thanks very much again. And yeah, looking forward to seeing the stuff on the internet.
Thank you very much.